Hey guys, I'm just gonna go through last year's waves systems paper. So yeah, right. So we're gonna assume that the speed of sound is 342 meters per second, and this question is about Sam's violin, and these 2 points are okay. So calculate the speed of the wave that travels along the string. Now this is a string, so we know that lambda equals 2L, and because it's playing the fundamental frequency, we just lambda is 2L. And we know that our frequency is 196 hertz. V equals F lambda, which is 2L times F, which is going to be 2 times 0.331 times 196, and this gives me 129.752 meters per second, which is 130 meters per second to three significant figures. And okay, analysis of the sound shows that it also vibrates at 392. So these are all multiples of the fundamental frequency. So to find out what one it is, we just go 588 over 196, which gives me the third harmonic. So this means that for a string, we will have two nodes. So that could be like here and here. And because it's a string, it'll start from here, and so it'll go up and down and then back and down like that. And then this one, the reflected wave. Okay, and that would look like that. And so here we've got a node, and then we've got antinodes here, we've got antinodes here, and we've got antinodes here. So that is this one there done. Okay, so Sam plays her violin. Okay, calculate the frequency recorded by microphone A. So the velocity of the source relative to A is going to be negative. Therefore, we know that our apparent frequency is going to be F times the wave velocity over so the wave velocity minus Vs, which is just going to be 196. And then using I think it was 342. Yep, using 342 on 342 minus 5.3, and that gives me that gives me 199.1 hertz, which is 199 hertz to three significant figures. Microphone B is directly behind, whereas mic indirectly in front. Okay, seven. Okay, the violin affects the frequency. So the motion of the trailer has nothing to do with the frequency, so we can just write that F is constant. Um, the speed of sound is not dependent on the motion of the trailer, and so we can write VW is also constant. The wavelength, so in front, right? So basically, um, in front of the trailer, the waves the waves each like wavefront will be compressed, right? So I'll show you what I mean, right? So say like there's this trailer Sam is sitting on, so these are going to be the sound waves, right? Um, there we go. And like basically the distance between that is going to be a wavelength. And then behind, it's going to get a lot larger, right? And so that's going to be your new lambda for this behind the car. So basically, in front of the trailer, the waves will be compressed, right? And this results in a smaller wavelength, right? Or lambda. Um, and that is V equals F lambda. And no, a decrease in lambda means an increase in frequency. Okay. And so basically for behind the trailer, and so we can just write that behind the okay, so we've answered this part and this part, and we've answered about the wavelength, and now we're just gonna answer about this part here. This means that um, B will record a lower frequency than the source, right? 6. And A will detect a frequency greater than 196 hertz. So yeah, that's pretty much this one in a nutshell. But yeah, right, on to the next question. Okay, question 2, violin tuning. Okay, alright. So we knew from the first question that lambda equals 2L, right? So if you increase L, then you also increase lambda, and as V equals F lambda, an increase in lambda means a decrease in F, therefore F decreases. Same uses a tuning fork that will always vibrate at 196 hertz. Okay, and here's a beat. So basically, right, like for beats, it's like when two waves of slightly differing frequencies combine, you get a resultant wave that has oh, of and large amplitudes. Um, this results in a wobble of loud and soft sounds which are known as beats. Cool. And yeah, so we've done that one. So Sam hears a beat of 196 hertz. So that would be 196 plus or minus 2.1 hertz. Which will be which would correspond to 198.1 hertz, or 193.9 hertz. She increases the speed of the wave along the string by increasing the tension in the string, and the beat frequency increases. Okay, so we know that the FB, the absolute of FB, is F1 minus F2, but in this case, we know that this one is constant, right? So it'll always vibrate. Minus 196, right? Determine it what. Okay, so that means if this one increased. So this is before. So before we knew that the beat frequency was 2.1 hertz, right? So we can just go to, before it would have been like this, 2.1 is equal to F1 minus 196. Therefore, our initial frequency would have been just 198.1 hertz. And and so for this one, explain what Sam must do. So basically she should decreasing she should decrease tension, which lowers V, and so F decreases equals F lambda. And we know that the velocity of the wave, no, the velocity of the wave is proportional to the tension as per this part here, by increasing the tension in the string. How will she know the string is vibrating at 196 hertz? No beats will be. Okay, so so this phenomenon is known as resonance. And basically the whole idea behind resonance is like when the frequency of the violin is equal to the natural frequency of uh the wine glass, right? And this isn't, by the way, this isn't how I'd write it in the actual exam. I'd put this into words, but like just to go over this, I'll just summarize it. So it's basically like when the frequency of the violin matches the natural frequency of the wine glass, and basically, this would result in a larger amplitude, basically, as they combine. This would result in larger amplitude, causing uh, the glass to rattle more intensely, more intense uh, time. And oh, right. So we've done that, and to stop it, she could like use some sort of like cushioning material or something like that, or like fill it with water. So she could fill the cup with water to absorb the energy. So yeah, that's that one. Um, Question 3, diffraction glasses. Okay, so at a fair, children are buying rainbow glasses made of diffraction gratings in a cardboard frame. Okay, so, alright, okay. So diffraction is basically the spread of waves through through a gap. Diffraction is the spread of waves through a gap. Okay. Give an in-depth explanation why this pattern is observed by. Okay, explaining how diffraction and interference cause bright spots. Okay, so basically what happens is that I'm just gonna put this in bullet points, but when waves, I should plug in my laptop too. Um, so when waves arrive in phase, right? Then their amplitudes add up basically, and this results in this basically results in right spot. And we should also note that like your n is like going to be a whole number, so n will be whole number. So yeah, there's that one. This is what, constructive interference. Yep. Um, yeah, so that's for the bright spots. And basically, and for the other one, for its opposite part, is when waves arrive out of phase, right? By 180 degrees. They cancel, and that results in zero amplitude. And so this means it's gonna be a dark spot, right? And so we know that this one is like a diffraction grating, so it's like there's gonna be like a bunch of like tiny little like gratings for light to pass through. Um, so as basically, right, like as this is like a diffraction grating, there are multiple slits. So here are your keywords: multiple slits. There's multiple slits. So like basically, there's gonna be more waves arriving out of phase, and basically this results in more dark spots, right? Okay, yeah. C. Calculate the slit separation in the grading. Okay, alright. Yeah, let's just make like a little bit of a diagram from this, but basically it was like um I think what was that like 1.75, and the wall is 1.43 meters from the grading. Okay, so this is gonna be 1.43 and this is gonna be 1.75, and this angle here is going to be theta. And theta will just be the inverse tan of 1.75 on 1.43 slit separation. So because this is diffraction grating, we just say n lambda equals d sine theta, and we are looking for d. And so we just write that d equals n lambda on sine theta. So our lambda, let's see, okay, so the second, so we know that n equals 2. Um, oh, sorry. So this is just going to be 2 bracket, and then our wavelength was 6.43 times 10 minus 7, I think, on, and hold on, let me just double check. Yeah, and working out the inverse tan of 1.75 on 1.43 in degrees gives me 50.746. So sine of 50.746, and that is just going to give me, and putting that all in my calculator gives me 1.66 times 10 to the minus 6 meters for the slit separation in the grating. Okay, so when the children look at the spot of white light, they see what with the spectra. Okay, so basically for this one, right, we know that n lambda equals d sine theta, right? So basically, what we have to look at here is that lambda is proportional to sine theta. Um, and so we know that violet has got the largest wavelength, right? So, no, sorry, violet has the smallest wavelength. Yeah, that's right. Violet has the smallest wavelength. So our spectrum usually stretches from violet to red, right? And so this has got uh, the smallest, this the smallest wavelength, and this has got the largest wavelength, red. So basically, um, smaller lambda, like violet, will be closer to n equals 0, right? So basically, n equals 0 will be this like white line, right? So n equals 0, and then we're gonna have like this section of light here, right? N equals 1, we'll call it. Um, and basically this is going to be, oh, hold on, what I'll do, I'll just change up the colors. So it's like we're gonna have red here, right? We're gonna have this line of red here, and then on this other end we'd have a line of like purple mostly, and basically in between we're gonna have like other colors, right? So, and we'll just write like other colors, right? Between this, um, like orange, yellow, green, blue, indigo, and then we'll have violet here. So, and then and we can write that larger lambda, like red, will be further, right? Because as lambda increases, so will sine theta. And so basically that's like, it's going to be further from this n equals 0 point here. So, and that would be on the left hand side, and same thing for the right hand side, n equals 1, but except this time red is going to be far on this side, and then we're going to have the same purple on this side and other colors. Like basically going in the order, like from, it would be like red, orange, yellow, green, blue, indigo, and violet. Oops. and basically the same sort of symmetry on the other side. But yeah, that's for this question here. Pretty much we answer all the questions. So yeah, that helps. Thanks for watching.